Hello everyone, welcome back to the Avinash Explains Tech YouTube channel and our Microservices Masterclass. In previous episode we discussed synchronous communication using REST and gRPC. In synchronous communication, one service sends a request and wait for another service to respond. But should a service always wait? Suppose the order service creates an order. After that, it needs to send a confirmation email, update inventory, notify the shipping system, generate an invoice, update analytics. If order service calls all of these services synchronously, the customer may have to wait several seconds or maybe in a minute. More importantly, even one dependent service is unavailable, the entire order request could fail. This is where asynchronous communication becomes useful. We will create this video in a two-part. In the first part, we will discuss what asynchronous communication means, synchronous versus asynchronous communication, message broker architecture, point-to-point and publish-subscribe messaging, Apache Kafka architecture, RabbitMQ architecture, and Kafka versus RabbitMQ. So let's begin with a basic concept. What is asynchronous communication? Asynchronous communication means that a producer sends a message without waiting for the consumer to process it immediately. The producer publishes the message to an intermediary called a message broker. The broker stores the message and makes it available to the appropriate consumer. The producer can then continue to its own work. The basic flow is producer sends a message to the message broker and message broker sends the message to the consumer. So let's understand this with a real world example. Imagine that you want to send some information to your colleague. You have two options. The first option is to call your colleague. You must wait for your colleague to answer the phone, and this is synchronous communication. The next option is send an email. After sending it, you can continue your work. Your colleague can read and process the email later. This is asynchronous communication. And a message broker also works somewhat like the email server. It receives the message from a sender, stores it, and delivers it to the recipient. Now let's apply this to an e-commerce system. When a customer creates an order, the order service stores the order in its database and publish an event like event type, order created with order ID, customer ID, and with the amount. After publishing this event, the order service can return a successful response to the customer that it does not need to wait for every downstream service. The inventory service can consume the event and reserve the product. The notification service can send a confirmation email. The analytics service can update its report. The shipping service can begin its workflow. All these consumers can process the same event independently, and this reduces direct dependency between services. The order service does not necessarily need to know how notification service works, where it deployed. It only needs to publish the correct event. This is called loose coupling. However, asynchronous communication also changes the way we design the system. The processing may not be completed immediately. Different services may temporarily have different views of data. This leads to a concept called eventual consistency, which we will discuss in a greater detail in a later episode. Now let's see now let's see the synchronous versus asynchronous communication. Let's compare two communication style. Synchronous communication. In synchronous communication, the caller sends a request and wait for a response, right? For example, the order service calls the payment service. Order service calls the payment service. The order service cannot complete the order until it receives the payment result. This approach is appropriate when the caller genuinely needs the immediate answer. For example, validating login credentials, checking the latest account balance, processing a payment before confirming an order, retrieving product information for the screen, validating whether a coupon is still active or not. In this situation, continuing without a result may not be possible, but synchronous communication creates temporal coupling. Temporal coupling means that both services must be available at the same time. If the payment service is slow, the order service also becomes slow. If the payment service is unavailable, the order service may fail, right? The second is, now let's discuss the asynchronous communication. In asynchronous communication, the producer publishes a message and continue processing. The consumer process the message independently. For example, order service creates an event and send to the message broker, and message broker send to the notification service, right? So order service does not wait for the email to be sent before confirming the order. If the notification service is temporarily unavailable, the message can remain inside the broker. When notification service became available again, it can process the pending messages. This improves resilience. It can also help absorb traffic spikes. Suppose your application normally receives 100 orders per minute, but during a flash sale, it receives 10,000 orders per minute. The order service can publish message quickly. The consumers can process the accumulated message at their own speed. We can also add more consumer instances to the increase processing capacity, right? The broker acts as a buffer between producer and consumer. But asynchronous communication is not automatically better for every requirement. If the customer asks why my payment is successful, was my payment successful, we usually need an immediate response. If the requirement is send a confirmation email after successful payment, asynchronous communication is more appropriate. A production microservice architecture generally use both styles. Use synchronous communication when an immediate result is required. Use asynchronous communication when work can happen later or when multiple independent services must react to an event. Now let's see the message broker architecture. We will understand core components of the messaging system. There are 4 independent elements: producer, message broker, queue or topic, and consumer. Who is the producer? Producer creates and publishes messages. For example, when order is created, the order service acts as a producer. It may publish an order created event, and the producer generally does not perform the consumer's work. It only communicates that something has happened and some work needs to be performed. And the next is message broker. The message broker receives a message from producer and routes or store them. Kafka and RabbitMQ are both message broker, but they store and deliver message differently. The broker provides a boundary between producer and consumer. Without a broker, order service might call the notification service directly. With a broker, the order service only publishes a message. The notification service consumes it independently. The next is queue and topic. Queue or topic. A queue or topic is logical destination where messages are placed. In traditional work queue, a message is normally processed by one consumer. A topic based system, the same event can be delivered to the multiple subscriber or consumer group. The exact behavior depends on the broker and messaging model. And the last part is consumer reads and process the messages. For example, notification service may consumes an order created an event and sends the email. After successfully processing the message, the consumer records and communicates its processing progress. In RabbitMQ, a consumer commonly sends an acknowledgement. In Kafka, consumers track their progress through the offset. We will discuss acknowledgements and offsets more deeply in part 2. Now let's see the next point, messaging patterns. There are two important messaging patterns, point to point and publish subscribe. What is point to point? In point to point messaging, a producer sends a message to a queue and one consumer processes that message. There may be a multiple consumer instances connected to the queue, but one specific message is normally handled by only one of them. Let's see example. Suppose an image processing service receives a request to resize an uploaded image. The application places an image resize request message in the queue. We may have 5 worker instance. Listening to that queue, one worker receives the first message, another worker receives the second message, and so on. This distributes the workload across the workers, and this is why this pattern is also called work queue or competing consumers pattern. It is useful for image processing, PDF generation, sending individual emails, background jobs, video conversion, report generation. This purpose is to distribute tasks, not to send every message to every consumer. The purpose is to distribute tasks, not to send every message to every consumer. Okay. The next one is publish and subscribe. In publish and subscribe messaging, a producer publishes an event. The multiple subscriber can receive it. Let's return to the order created event. The inventory service needs it to reserve the product. Notification service needs it to send an email. Shipping service needs it to prepare delivery. The analytics service needs it to update business report. Each of these services needs its own copy or independent view of the event. That is publish subscribe communication. This pattern is useful when one business event must trigger multiple independent actions. The common mistake is to treat a business event like a command. A command tells a specific consumer what to do, send order confirmation email. An event describes something that has already happened, order created. Commands are usually directed towards a particular responsibility. Events can be consumed by any interested service. This distinction makes an event-driven system easier to understand and evolve. Now let's see the Apache Kafka architecture. Kafka is a distributed event streaming platform designed for high throughput and durable event processing. Its main component includes producer, topic, partition, broker, consumer, consumer group, offset. A produce sorry What is producer? A Kafka producer publishes a record to a topic. For example, the order service may publish event to topic named order events. What is topic? A topic is a named stream of records. It is similar to a category. All events related to order may be published to the order events, while payment related events may go to the payment events. A Kafka topic is divided into partitions. What is partitions? Partitions allow Kafka to distribute data and processing across multiple machines. Suppose the order events topic has three partitions: partition 0, partition 1, partition 2. Different messages can be written to different partitions. This allows multiple consumers to process events in a parallel. Kafka guarantees ordering within a partition, not across the entire topic. For example, if all events for order ORD 5001 must remain in order, we can use the order ID and as the message key. Kafka will consistently send a message with that key to the same partition. Therefore, events such as order created, payment completed, order shipped, order delivered can remain ordered for that particular order. But we should not assume a global order across all partitions. What is broker? A Kafka server is called a broker. The Kafka cluster normally contains multiple brokers. Partitions are distributed across these brokers, which helps Kafka scale horizontally. Kafka can also replicate partitions so that data remain available in a broker fields. For example, with a replication factor of 3, Kafka maintains copies of partition of 3 brokers. One replica act as a leader and the other act as a follower. Next is consumer. A consumer reads records from a Kafka topic. Kafka does not normally remove an event simply. Let's see what is consumer. A consumer reads records from a Kafka topics. Kafka does not normally remove an event simply because one consumer has read it. Instead, event remain available according to the configured retention policy. Retention may be based on time, size, or compaction rules. This allows consumer to replay order events when necessary. For example, suppose we develop a new fraud detection service today, but order events have been retained for the last 7 days. The new service can process those older events to build its initial data and reconstruct the state. This replay capability is one of the Kafka's strongest features. Now next is a consumer group. Consumers can organize into consumer groups. Within one consumer group, a partition is processed by only one consumer instance at a time. Suppose a topic has 3 partitions and consumer group has 3 consumers. Each consumer can process one partition in parallel. If we add a 4th consumer to that same group, one consumer may remain idle because there are only 3 partitions. This is why the number of partitions affect the maximum parallelism of a consumer group. Different consumer group can read the same event independently. For example, the inventory service has one consumer group, the notification service has another consumer group, the analytics service has another consumer group. Each group receives and processes the order events independently. Okay, now let's see what is offset. An offset is a position of records within a partition. Consumers use offset to track how far they have processed. If consumer restarts, it can continue from the last committed offset. Offset management is extremely important. If an offset is committed before business processing complete, if an offset is committed before business processing complete, a failure may cause massive loss from a consumer perspective. If it is consumed after processing, the message may be processed again if the application crashes between processing and committing. That's why Kafka consumers must generally be designed to handle duplicate processing safely. We will cover that through the idempotency in the part 2. Now let's see the RabbitMQ architecture. RabbitMQ is a message broker that particularly strong in message routing and work queue scenarios. Its primary components are producer, exchange, binding, queue, and consumer. Who is the producer? Producer send a message to an exchange. This is an important difference in the typical RabbitMQ model. The producer does not publish directly to the queue, it publishes to an exchange. And what is exchange? Exchange examines routing information, decide which queue or queues should receive the message. This makes RabbitMQ routing very flexible. And what is binding? A binding is a routing relationship between exchange and a queue. This tells exchange how message should be routed. Depending on the exchange type, decision may use a routing key or mechanism patterns. What is queue? Queue is store the message until consumers process it. A queue can leave one consumer, multiple competing consumers. And what is consumer? Consumer receives a message from the queue and process them. After successful processing, consumer normally sends an acknowledgement. Once the broker receives the acknowledgement, it can remove the message from the queue if the consumer fails before acknowledgement. If the consumer fails before acknowledgement, the RabbitMQ can make the message available for redelivery, depending on the configuration. RabbitMQ exchange type. RabbitMQ supports different exchange type. Direct exchange. A direct exchange routes a message when its routing key exactly matches the queue binding key. For example, a message with the routing key payment.success can be routed to the queue that bound using the same key. This is useful when you know exact destination category. Topic key. A topic exchange uses pattern based routing. For example, order created, order cancelled, payment completed. The queue may subscribe order.star. It can receive multiple types of the order related messages. This provides more flexible routing than exact match. And fanout exchange broadcasts every message to all queue bound to it. It ignores the routing key. What is the difference between Kafka and RabbitMQ? So now we have reached the most common question: should we use Kafka or RabbitMQ? There is no universal winner. The correct choice depends on what the system needs. Messaging model: Kafka behaves like distributed commit log. Events are appended to the partition and retained according to the policy. Consumers track their own positions using offset. RabbitMQ is centered around exchange, queue, and message delivery. Messages are routed to the queue, consumed, and typically removed after acknowledgement. Throughput: Kafka is designed for extremely high throughput event streaming, and it works particularly well when a large volume of event must be stored, processed, and replayed. RabbitMQ also provides good performance, but it's often selected for flexible routing, work distributed and traditional message queue. We should not make a decision based on only one on the benchmark. Actual performance depend on payload size, durability setting, acknowledgements, hardware and application design. Message retention and replay. Kafka normally retains messages even after consumer process them. This allows multiple consumers to read same events at different times and enables historical replay. RabbitMQ typically keeps a message in a queue until it's acknowledged or expires. After successful acknowledgement, the message is usually removed from the queue. RabbitMQ can support redelivery or other patterns, but historical replay is not its primary model. Routing. Kafka routing is comparatively simple. Producers choose a topic and a key to determine the pattern. RabbitMQ produces advanced routing through the direct topic, fanout and headers exchange. If complex routing rules are major requirement, RabbitMQ is often easier to use. And the consumer model, Kafka consumer groups provide scalable stream processing. Different groups can independently consume same events. RabbitMQ commonly distribute messages among competing consumers attached to a queue. To send the same message to multiple applications in RabbitMQ, we generally create separate queue and bind them appropriately to an exchange. When should we use Kafka? Kafka is a strong choice for event streaming, analytics pipeline, application activity tracking, log aggregation, change, data capture, event sourcing, high volume stream integration, scenarios requiring event replay, building real-time data pipelines. Okay, when we should choose the RabbitMQ? We should choose the RabbitMQ for the background job processing, task distribution, complex message routing, work queues, command-based messaging, per message acknowledgement, request reply message systems where messages should be processed and removed. Can we use both? Yes, we can use the both. Okay. So let's summarize what we learned. Asynchronous communication allow a producer to publish a message and continue without waiting for a consumer. A message broker decouples producer and consumers and can absorb temporary traffic spikes. Point-to-point message distribute individual tasks among consumers. Publish subscribe allow multiple independent system to react to a same event. Kafka is a distributed event streaming platform built around topic, partition, offset and consumer groups. RabbitMQ is a message broker built around exchanges, binding queue and consumers. Kafka is especially effective for high volume event stream retention and replay. RabbitMQ is especially effective for the work queue and flexible message routing. The right choice depends on your use cases, not on which technology is more popular. This completes part 1 of asynchronous communication in microservices, but publishing a message is only the beginning. What happens when consumer fails while processing a message? Should we retry it? What happens if the same message is delivered twice? How do we preserve message ordering? What is DLQ, dead letter queue? And can we really guarantee exactly once processing? We will answer all of these questions in part 2. Okay. If this video helped you, please like it, share it and subscribe to the Avinash Explains Tech YouTube channel. Also let me know in the comments for your current use cases. Would you choose Kafka or RabbitMQ and why? Thank you for watching. Keep learning, keep building. I'll see you in the next part 2. Thank you so much.